Everything we did in the last section works really well when you have these small systems with just two equations, two variables. But once you start to introduce bigger systems with more variables, more equations, keeping track of everything can become sort of a mess. So our goal in this next section is to introduce matrices, which are, at least for systems of equations, provide a really nice notational framework to work in. So before we get into that, let's just take a slight detour into what a matrix is. And a matrix is really nothing other than a rectangular array of numbers. So behind me I have two examples of matrices, a rectangular array of numbers, and another example, a rectangular array of numbers. So this is all that a matrix is. One of the most important properties of a matrix is the size of the matrix. Of course, you can see these are somewhat different matrices in the fact that here I have 2 rows and 3 columns, and over here I have 3 rows and 3 columns. So we tend to denote the size of a matrix by exactly what I just said, the rows by the columns. So this would be a 2 by 3 matrix. It's always rows by columns. Alright, so rows first, then columns. And this is, of course, 3 rows, 3 columns. This is a 3 by 3 matrix. Once again, 3 rows, 3 columns. And the other interesting bit of information in a matrix is what the individual numbers are, right? So these numbers are often called the entries or the elements of the matrix. And where should I write this? Let's see. Let's say we track. Nah, I do like the word denote. We denote the element or entry in the ith row and jth column of a matrix using double subscript notation. So by a sub I j. So the first number there, the I, tells you which row it is, which row it comes from, and the second number, j, tells you which column it comes from. So for example, in this matrix, let's just say I want the element A, 2, 3. Well, the element A, 2, 3, so I'm looking for the element in the second row and the third column. Second row, third column would be this guy. So that's the number 2. And over here, how about we come in and we ask, what's A31? So this would be the element in the third row, first column. That's this entry right here. That's just 1.6. And then you'll notice in the second matrix, I've introduced some stranger numbers. I've got 1.6 in here. I've got pi. These can be any numbers at all that you want. They just have to be real numbers. But usually they'll be integers, but it will often have fractions as well. So typically they will at least be rational numbers. We won't often see irrational numbers in our matrices. So this is a matrix, and I'm going to tell you what we're going to do with matrices in this section. Well, actually, I got a little bit ahead of myself. There's one more thing I want to tell you, just a little bit more notation. Here's a matrix, 1, 2, 0, minus 4. What size is this? It's got 1 row, 4 columns, so this is a 1 by 4 matrix. But because it has only a single row, we often call matrices of this form, we'll call this a row matrix. The whole thing is a row matrix. So this is just a matrix with 1 row. Let's just say 1 by m. 1 by n. And so anytime you have a matrix with just 1 row, so it's size 1 by n, then it's a row matrix. And similarly, here's 1, 2, 3, 4. Let's just go 1, 2, 3. So this is how many rows? 3 rows, 1 column. Got a single column to it. This is a column matrix. So this would be m by, m by 1. So anytime you have a matrix with just a single column, it's called a column matrix. Not terminology we'll use in this section, I don't think, but terminology I want to introduce anyway. So these are row matrices and column matrices. And I guess one more thing I'll point out, here's 2, 0, minus 4, minus 1. This is, of course, 2 by 2. But anytime your number of rows and number of columns match up, we often call these square matrices. So this is a square matrix. Alright, so this would just be n by n. The first two examples I had on the board, the second one was 3 by 3, so that's also a square matrix, right? Anytime the number of columns and rows have the same values. So anyway, just a little bit more terminology. Now I'll tell you sort of why we're going to use matrices. So our goal, at least in this section, is to simplify or to streamline our method of elimination using simplified notation. So again, it wasn't really necessary when we're working with small systems, these two equations, two variables. It wasn't really necessary, but once you start getting up to 5 or 6 equations, lots of 5 or 6 variables, everything can become sort of a mess to track. So we're going to simplify our notation a little bit, and what we're going to do is we're going to replace our systems. We'll start off with a system of equations, and we'll replace it by what's called an augmented matrix. So for example, here's a system. The system, and I'm not going to use the variables x and y anymore. Again, when you start getting lots and lots of variables, you run out of letters pretty quickly, x, y, z, and so on. So I'm just going to start calling them x1 and x2, and x3 if I have more, but in this case it's x1 and x2. So x1 plus 4x2 equals 14, and 3x1 minus 2x2 equals 0. Alright, so here's my system. Again, instead of using the variables x and y, I'm just using the variables x1 and x2. But here's my system. Here's the augmented matrix. So it's going to be a matrix with 2 rows because I've got 2 equations, and I use this row terminology in the last section. So 2 equations means I have 2 rows, and my columns, the columns are going to be the coefficients of the variables and the constants. So my first column essentially corresponds to the x1 variable, the coefficients of x1. So 1 and 3. So I'm going to put 1 and 3 here. The next column is my x2 column. I've got the coefficients are 4 and, in fact, not 2, this is minus 2, right? So 4 and minus 2. And then I've got my constants, 14 and 0. So corresponding to this system, I've got this, this 2 by 3 matrix, and what makes it an augmented matrix is really this is just a notational device. It doesn't mean anything other than it indicates the fact that this is where my equal sign is. We usually put a little bar right there. Right, so it's just a notational device to tell me, okay, everything to the right of this bar, these are my constants on the right-hand side of the equation. Okay, so we form a matrix where the columns are the coefficients of the corresponding variable. So in this case, I've got the coefficients of the x1 variable, and in the second column I've got the coefficients of the x2 variable, and lastly I've got the constants on the right hand side of the equals sign. And this already looks a little bit more compact because you'll remember sort of when we're solving these systems using elimination, do I really need to keep track of the actual variable names? Well, no. So as long as I line them up sort of by column, I already know which variables I'm looking at. all I really care about is the coefficients in front of them. So this is keeping track of all of the relevant information, all of the important information that I need, and we're keeping track of which coefficient corresponds to which variable by putting them all in the same column. And so this is just, this is the augmented matrix for the following system, or for the above system. Let's do a few more. Alright, so here's two more systems, and we're just going to build the augmented matrices for these really quickly. Then I'll tell you sort of what we're going to do with the augmented matrices. But just to make sure we understand this process, here's another system, two equations, two variables. So my first column is going to be the coefficients of the x1 variable, so 2 and 3. So my first column is 2, 3. Second column, coefficients of the x2 variable, -3 and -4. And last but not least, I'm going to put my augmentation bar there to indicate I've got my equal sign. And to the right of that, I've got -6 and -6. And you'll notice that really does convey all of the information. This is a reversible process. If I gave you the augmentation or the augmented matrix, you could reverse this and you could say, okay, this is the equation 2x1 minus 3x2 equals 6. And my second equation is 3x1 minus 4x2 equals -6. So all of the information is there in a more compact way. Similarly, this is actually 3 equations, and you'll notice there's 3 variables. I've got x1, x2, and x3. We're not going to work with systems this big in this section, we will in the next, but might as well practice building a matrix. I'm going to have 3 rows, because I've got 3 equations. My first column is coefficients of x1. I've got 2, 1, 1. Second column, coefficients of x2. I've got -1. And it's not written in this equation because x2 in this equation doesn't exist, but you can think of this as plus 0 times x2 if you want, right? So the coefficient of x2 in this equation is 0, because there are no x2s, and then plus 2. So 2 in the third one. And now the same thing's happening up here in the first equation. I don't have any x3s, I've got 0 x3s, so I've got 0, 1, and this equation doesn't have any x3s either, so 0. Then I've got my augmentation bar, the equal sign, and we've got 0, 1, 8. And once again, this is completely reversible as long as we agree that the first column is the coefficients of x1, second column is the coefficients of x2, third column is the coefficients of x3, and there's my constants. You can read off the exact same equations. 2x1 minus x2 plus 0x3 equals 0. There's the first equation. Similarly for the second and third. Alright, so this is a completely reversible process, and that's important. Alright, so we had allowable operations that we were allowed to do with our systems of equations that preserved the solution set, that gave us an equivalent system, right? We were able to interchange equations in the system, we were able to multiply equations on both sides by a non-zero multiple, and we were able to add equations together, or add one multiple of an equation to another equation, and that gave us an equivalent system that didn't change the solution set. We want to do the same thing here with our augmented matrices, remembering that the matrix just represents an underlying system, right? So we say the two augmented matrices are row equivalent, so the matrices are row equivalent if they represent equivalent systems of equations. So if they represent systems of equations that have the same solution set. And we're allowed to perform the following operations to produce row equivalent matrices. And these are exactly the same as our operations on the systems themselves, on the equations themselves. They represent exactly the same thing. So, for example, I can interchange any 2 rows in my augmented matrix, because that corresponds to just interchanging two equations in the system. We can replace a row by a non-zero multiple of the row. So this non-zero multiple k of that row replaces the row. And again, this corresponds to just multiplying an entire equation by a non-zero multiple. And we can replace a row by the sum of that row and a constant non-zero multiple of another row. So row I plus a constant times row j replaces row I. And this is exactly the same as before, just realizing that when I'm working with the rows of my matrices, it represents sort of the exact same operation on the underlying equation. So let's do a few examples. Alright, so our first example is just an example of these row operations. Here's the question: apply the row operation R2, row 2 minus 4 times row 1 replaces row 2 on the following augmented matrix. So this means I'm going to take row 2, I'm going to subtract 4 times row 1 from it, and that will become our new R2. So let's see. Notice I'm only replacing row 2, so that means row 1 stays exactly the same. So I'm just going to copy row 1 again. 1 minus 2 and 2. But now row 2 is getting replaced. It's getting replaced by row 2 minus 4 times row 1. So let's see, what do we have? We've got 3, and I'm going to subtract from it the corresponding entry above it. So 3 minus 4 times 1. 3 minus 4 times 1, 3 minus 4 is minus 1. And that's all there is to it, right? It's 3 minus 4 times this entry. Here I've got minus 5 minus 4 times minus 2. Minus 5 minus 4 times minus 2 is minus 8. Minus 5 minus minus 8 is minus 5 plus 8 is 3. Lots of negatives there. But I'm taking this entry and I'm subtracting from it 4 times the entry in row 1. And last but not least, we've got this entry, 9 minus 4 times 2, so 9 minus 8 is 1. And that's all there is to it. That's the result of applying this row operation. Underlying, remember there's an underlying equation here. This is 3 times x1 minus 5 times x2 equals 9. And I'm just saying I'm going to take that equation and I'm going to subtract from it 4 times this equation in row 1. The notation people usually use is this augmented matrix here is row equivalent to this one, so I'm going to say it's row equivalent using just this little squiggly tilde to indicate this is row equivalent to this. And why don't we write down the operation we did to keep track of things. R2 minus 4 times R1 replaces R2. So there's an example of a row operation. We're going to do a whole bunch of these because we're going to solve systems by applying row operations. So let's jump straight into that. Let's solve a system. Okay, so here's our system. We've got the system 2x1 minus x2 equals minus 7, and x1 plus 2x2 equals 4. And there's many ways you could solve this. Of course, you can solve this using just standard elimination or substitution or whatever, but we're going to solve this using augmented matrix methods. And again, I want to point out that yes, you probably could do this faster just using standard elimination or substitution in this case because it's a small system, but when you get to larger systems, the augmented matrix stuff really is very nice. So we're doing this on small systems right now just to learn how to do it, but we're doing it because it becomes nice when you have big systems. So let's see. This gives us the following augmented matrix. What do we have? We've got 2 and 1, 2, 1, minus 1 and 2 in our second column. Augmentation bar, minus 7 and 4. And I'll tell you what the goal is. Goal is to reduce this, to apply row reduction techniques, to reduce it to the following form. Reduce to the form 1, 0, 0, 1, and some constant if possible. We'll formalize exactly how to do this in the next section, but this is what we're going to try to do sort of informally right now, is reduce to this form. Apply row operation techniques to make this look like this if we can. Why do I want to reduce it to that? Well, think about what the underlying system here would be. The underlying system here would be, if I can reduce it to this, I would just have 1 times x1, so x1 plus 0 equals m, and 0 times x1 plus 1 times x2 equals n. And then there's nothing to do. That's my solution, right? This is the solution. x1 equals m, and x2 equals n. Again, we used to call these x and y, but now it's our variables x1, x2. But there's my solution. So if I can transform this into this, then I have my solution staring me in the face. So that's what we're going to try to do. The question is, how do we do it? And it turns out it's very algorithmic. I'll give you the exact algorithm next time. But here let's try and just sort of freeform this. So what do I want? Well, the first thing I always want is we work with the left-hand corner, the top left-hand corner. I want a 1 right there. How do I get a 1? A couple of ways I could do this. I could divide this first row by 2. That would put a 1 there. But notice that would also introduce fractions. I'd have minus 1/2, I'd have minus 7/2. And although there's nothing wrong with fractions, you tend to want to avoid them for as long as you can because they make the arithmetic sort of messy. So there's another way I could get a 1 up here. I could subtract the second row from the first one. That would put a 1 right there. But even easier, I can just interchange these two rows. So let's just do that. Let's row 1 and row 2 will interchange here. So we'll have 1, 2, 4, 2, minus 1, minus 7. Easy. Okay. I've interchanged my two rows. I've put a 1 right there. Now it turns out the next thing you want to do is always work down from there. I have a 0. I have a 0 below the 1. And this is usually how we'll proceed. In fact, always how we'll proceed is I want to put zeros always below this this leading 1, or this leftmost 1. So I want to 0 this entry out. How do I 0 this entry out? Well, I need to add or subtract an appropriate multiple of row 1 to this row to put a 0 right here. So how do I do that? Well, I already have 1 up here, so it's easy to see what I need to do. I need to subtract, since this is 2, I need to subtract twice the first row from the second row. So we're going to do row 2 minus 2 times row 1 is going to replace row 2, or become our new row 2. So row 1 doesn't change. This is still 1, 2, 4. But row 2, I'm subtracting twice row 1 from it. So 2 minus 2 times 1 is 0, just like I wanted. If I don't have a 0 right there, I'm not doing what I want, because that's my goal, is to put a 0 right there. And then whatever follows, whatever happens to the rest of it is whatever happens. Here I've got minus 1 minus 2 times 2, minus 1 minus 4 is minus 5. And I've got minus 7 minus 2 times 4, minus 7 minus 8 is minus 15. Great. What do I want to do now? Well, we have a 1 right there, we have zeros all below it. It turns out in our algorithm we're going to say, alright, so now that I've dealt with that and I've put zeros below it, we're just going to ignore this top row. We're going to ignore this top row and look at the remaining submatrix and repeat the process. My first entry in the next row, I want that to be a 1. So that means this guy right here, I want that to be a 1. Remember, we're trying to reduce this to 1, 0, 0, 1, so I want this to be a 1. How do I do that? Well, I could just divide this whole equation by minus 5, or that entire row by minus 5. So we'll do that. Let's do minus 1/5 row 2 will become our new row 2. So I've got 1, 2, 4, 0, 1, dividing by minus 5. And this is nice because this is an integer. Minus 15 over minus 5 is just 3. Cool. I'm being a little bit inconsistent here. Here I wrote my operation below the row equivalent sign. and here I wrote it above, but you know, I'm just indicating what I'm doing each step. So here I'll write it above again. What's our last step now? Last step now, I've got a 1 here, I've got zeros below it. In this row, my first entry is a 1. The last thing I need a 0 up here, right? I needed 1, 0, 0, 1. So how do I get a 0 right here? Well, I can subtract the appropriate multiple of row 2 from row 1. And the reason I can do this now, and the reason I had to put a 0 here first, is because now when I zero this thing out, when I subtract appropriate multiples of row 2, I have a 0 right here that's not going to mess with this 1. It's not going to change it. So that 1 is fixed, and then no adding of row 2 to row 1 will ever change the fact that this is a 1. So that will stay forever. Let's see, what do I want to do? I want a 0 right here, this is a 2, so I need to subtract twice the second row from the first one. So we're going to do row 1 minus 2 row 2 will become our new row 1. Row 2 isn't changing, so I'm just going to copy it down really quickly. 0, 1, 3. And up here, okay, I've got 1 minus 2 times 0 is 1. As promised, this is why we zeroed this out first, so it doesn't change now. Here I've got 2 minus 2 times 1 is 0, just like we wanted. And I've got 4 minus 2 times 3. 4 minus 6 is minus 2. And we've achieved our goal. We're in the form we wanted. 1, 0, 0, 1, and we've got constants on the right-hand side. So this tells me what my solution is. My solution is x1, right? This represents x1 equals minus 2. And this line, the underlying equation here, is x2 equals 3. I will say, at this point, it's worth checking. As you go through these steps, it's really easy to make copying errors. It's really not uncommon at all. I make these mistakes all the time. It's really easy to make copying errors with all these numbers or little arithmetic errors. So check that your solution works, because this takes just another 10 seconds. Plug in minus 2. 2 times minus 2 is minus 4. Minus 3 equals minus 7. Great. Satisfied that equation. Minus 2 plus 2 times 3 minus 2 plus 6 equals 4. Great. So now I know I didn't make any mistakes. That is indeed the solution. So this will sort of be our method every time. This particular form I have over here, this is an example of what's called in fact, I shouldn't just circle this, it's really the whole augmented matrix. This is an example of what's called being in reduced form. And I'll define precisely what reduced form is next time for larger matrices. But let's just do a few more examples using small systems for now. Okay, so here's our next example. We're asked to solve this following system. 2x1 minus x2 equals 3, and 4x1 minus 2x2 equals minus 1. So once again, we'll write down the augmented matrix. This will be the first thing we do. First column will be 2 and 4, coefficients of x1, coefficients of x2, minus 1, minus 2, equal sign, and then 3 and minus 1. Okay, let's see. What's our first step? Our first step, as always, I want to reduce this to 1, 0, 0, 1 if I can. My first step, as always, is to try and put a 1 up here. Last time we did it by interchanging 2 rows, but I don't have any rows with a 1 in this first column. I don't see any way to avoid it. We're just going to introduce fractions here. Let's just divide the first row by 2. Okay, so we're going to do 1/2 of row 2 will replace row 2. So divide the first row by 2 and get 1 minus 1/2, 3/2, and then 4 minus 2 minus 1. You generally want to avoid fractions as long as you can because they're not as nice to work with, but There was no easy way to avoid it here. Next up, what do I want to do? Next up, I want to put a 0 in all of the entries below this leftmost one. So I need to subtract 4 from the 4 times the first row from the second row. Because this is a 4, I need to have minus 4 times 1. So we'll do row 2 minus 4 times row 1 will replace our row 2. And that's going to give us what? Well, first row stays the same, so I'll just copy it down. Again, make sure you don't make copying errors there. 1 minus 1/2, 3/2. And let's see, I've got 4 minus 4 times 1. 4 minus 4 is 0, exactly as I wanted. I've got minus 2 minus 4 times 1/2. 4 times minus 1/2. 4 times minus 1/2 is minus 2. So minus 2 minus minus 2 is minus 2 plus 2 is 0. Again, a lot of negatives there, but yeah, it's minus 2 minus 4 times minus 1/2 becomes minus 2 plus 2 is 0. And then last but not least, I've got minus 1 minus 4 times 3/2. 4 times 3/2 is 6, so minus 1 minus 6 is minus 7. That's interesting. What does this say? Well, remember my goal. I wanted to reduce this to 1, 0, 0, 1, and there's no way to do that. There's no way to do that. I put a 0 right here. There's no way to put a 1 here now. Not that preserves this 0 as well. And think about what the underlying system here says. This equation, that says 0 equals minus 7. What does that mean? That's unsatisfiable, right? That's impossible. That means that this system has no solutions. So we're actually done right now. There's nothing else to do. It has no solutions. So sometimes you can't always reduce to the form we wanted, which was 1, 0, 0, 1, and 2 constants up here, m and n. Sometimes you end up in a situation like this, where you have all row, or a row of all zeros, an augmentation bar, and then a non-zero constant. Immediately when you run into that situation, you can stop. You can say, oh, well, I understand what this underlying equation is. It's 0 equals some constant, some non-zero constant, which means that's impossible. I have no solutions. So there is the answer to this one. And we'll do the last possible case. Alright, so one more example. We've got 2x1 minus x2 equals 4, minus 6x1 plus 3x2 equals minus 12. And we'll attempt to solve this using augmentation methods. So we'll write down the augmented matrix: 2 minus 6 minus 1, 3, 4, and minus 12. What do I want to do? This first entry up here in the top left, I want to make that a 1. See no great ways to do it, so I'm just going to divide by 2. So 1/2 of row 1 will become our new row 1. And that will give me 1 minus 1/2, 2, and minus 6, 3, minus 12. What now? Now I want to put a 0 below this entry. So how do I do that? Well, I've got a minus 6 here, so I need to add 6 times 1 to it. So we'll add 6 times the whole first row to the second row. So we'll do row 2 plus 6 times row 1. Row 1 is still the same, so we'll just copy it down again. What about row 2? Okay, so I've got minus 6 plus 6 times 1. So minus 6 plus 6 is 0, just like we wanted. Here I've got 3 plus 6 times minus 1/2. 6 times minus 1/2 is minus 3. 3 plus minus 3 is 0. And now this is interesting. If I have a non-zero constant over here, I know again I have no solutions. If this is non-zero, I have 0 equals something that's non-zero, we'll have no solutions. So we'll have to see what happens. I've got minus 12 plus 6 times 2. 6 times 2 is 12, minus 12 plus 12 is 0. Okay, so I have 0 equals 0, that's fine. That doesn't mean I have no solutions. We're actually in one of these cases where we've got rid of an equation entirely. These are two parallel lines. So all I have is this equation. My underlying equation that I'm left with is x1 minus 1/2 x2 equals 2. Well, what does this mean? This means I have infinitely many solutions, and I just have to choose a parameter. So let's say, how about I solve for x1? x1 is going to be 1/2 of x2 plus 2. So my parameter, let's let x2 be, choose a parameter, call it k. x2 is k. And then x1 is 1/2 of k plus 2. And there's my solutions. Usually you'd write these in the opposite order. You'd sort of interchange those, x1 first and then x2. But yeah, there's my solution set. Again, it's infinite. You choose a value for k, and that gives you values for x1 and x2. Again, you can write this as an ordered pair if you want. You can say, okay, this is 1/2 k plus 2 and k, if you want to give it like that. If you want to be extremely formal, you can write this using set builder notation, but this will suffice for us. There's my solutions to this system. So there's the third possible case. The first possible case is you reduce this to 1, 0, 0, 1 with m and n over here, and you have your unique solution that you can read off. The second possible case is you've got 1, 0, 0, 0, but then down here I've got a non-zero constant, and that immediately tells me I have no solutions. Or maybe you just reduce or get rid of an entire row, right? This row tells me nothing now, and you've got all zeros in a row. Well, now you're in this infinite solution case, and you have to choose a parameter. So just say, I'm going to let x2 be anything, and then I'll solve, so x2, give it a parameter named k, and then solve for x1 in terms of that parameter. So in our next section, we're going to really formalize this. This is what we've been doing is called Gauss-Jordan elimination. We're going to formalize the exact algorithm for how Gauss-Jordan elimination works and apply it to even larger systems. Thanks.